we need to briefly review what we know about pressure, what we know about gases, and what we know about gas laws and how they all relate. So we know that there are certain factors that influence the pressure of a gas. Volume, which we abbreviate V, the number of particles, which we abbreviate N, and the temperature, which is T. Now I'd like to point out, N, we always said before, was the number of particles. Now we've learned about moles, so this can also be our number of moles. Just a little tidbit, we'll need that later. So let's review how each of these things affect our pressure. Oh, first we have to talk about our units. Before we can start doing math problems, we need to make sure we have our units right. So just to refresh, ATM is atmospheres. We can have pressure in atmospheres. We can also have pressures in millimeters of mercury, or mmHg. Just stands for millimeters of mercury. Those are your two most common pressure units that you'll see in these problems. Our first relationship is pressure and volume, or PV. This is an inverse relationship. When we did this lab in class a long time ago, we graphed our relationship between pressure and volume. We saw that as we increased volume, we decreased pressure. So if volume goes up, pressure goes down. If volume goes down, so if it goes this way, if it gets smaller, our pressure goes up. So it's an inverse relationship. They're opposites. So a quick example problem. Calculate the new pressure if you increase volume from 2.5 liters to 5 liters, and your initial pressure is 2 atmospheres. So if our volume goes up, what do we expect our pressure to do? You should be saying we would expect our pressure to do the opposite. Our pressure should go down. So if we start with our initial pressure, our 2 atmospheres, we need to multiply it by some ratio that's going to make that number go down or get smaller. Our two options are either 2.5 over 5, or we could have done 2 atmospheres times 5 over 2.5. Now, you could either calculate this and realize that this one's wrong, or you could see that 5 over 2.5 is 2. That's going to make this number go up, so we're actually not going to use that one. We're going to use it this way. 2 atmospheres times 2.5 over 5 gets you 1 atmosphere, and that's our final answer. Next relationship. Our next relationship is the one between pressure and number of particles or number of moles. This is a direct relationship. As we increase our number of particles, our pressure goes up. If we were to decrease our number of particles, our pressure would go down. So they go the same direction. So again, let's work through a quick example problem. Calculate the new pressure if you decrease the number of particles from 12 to 4. So our N goes down. What would we expect our pressure to do? You should be saying we would expect our pressure to go down as well. Our initial pressure is 400 millimeters of mercury. Again, we're going to multiply it by some sort of factor, some sort of ratio that will make that number go down, because we said we wanted our pressure to get smaller. So are we going to multiply by 12 over 4 or 4 over 12? You should be saying 4 over 12. 4 over 12. There we go. This ratio will give us a smaller number. When you calculate this, you should get 133 millimeters of mercury, and that makes sense. We expected our pressure to go down. This is a lower pressure than where we started. Last relationship, pressure and temperature. So again, when we did this in lab, when we graphed pressure and temperature, we saw that we had a direct relationship. As our temperature goes up, our pressure goes up. As our temperature goes down, our pressure goes down. We had to note that in order for this to work, our temperature had to be in Kelvin. Not degrees Kelvin, just Kelvin, unit of temperature. To get to Kelvin, it was degrees Celsius plus 273, and that was our temperature in Kelvin. That's what moved this y-intercept down to 0. When we originally did this in lab, our graph looked like that. It was skewed. Quick example problem. Calculate the final temperature if the pressure rose from 1 atmosphere to 8 atmospheres. So our temperature went up. What do we expect our pressure to do? We should expect our pressure to go up. Our initial temperature is 298 Kelvin. We want that to go up, so we want the bigger number to be on top. So 1 atmosphere, or 8 atmospheres over 1 atmosphere. And when you calculate that, you get 2,384 Kelvin, which, by the way, is 2,111 degrees Celsius. Really hot. Oftentimes, you won't see a problem, or especially in a real-life application, where you only have one factor that's changing. You're probably changing multiple things. So let's look at a multi-factor problem. The question asks to calculate the final pressure if you increase the volume from 3 milliliters to 9 milliliters and increase the number of particles from 5 to 10. So our initial pressure is 0.8 atmospheres. We're going to multiply it by 2 factors. The first one, we're going to look at volume. Our volume went up, which means we need our pressure to go down. Since we need our pressure to go down, we need the smaller number on top. So we're going to put 3 milliliters over 9 milliliters. That'll make our pressure go down. Our second factor increased the number of particles from 5 to 10. So if our number went up, we would expect our pressure to go up. So we need to multiply by a factor that'll make our pressure increase. So we're going to put the bigger number on top and the smaller number on the bottom. When you plug this into your calculator and get a number out, you should get 0.53 atmospheres. So it did go down. This tells you that the volume had a bigger influence than the number of particles, because it made it go down. However, adding particles made the pressure go down not as much as it would have if you had only increased the volume. And that's our quick review of how you do gas law problems.